You look at the curve, more phase shift will be there, right? Actually, this one, at least it will be a pole, it just make it even smaller, huh? The UGF will increase, right? But for the RHP 0, it increases further UGF. Normally, we have wider UGF, you have wider phase shift, you have more phase shift, right? That's why I say this is worse than pole. Oh, but RHP 0, remember, L stands for love, you know? Then I think you won't confuse anymore in life, you know, which one. That's why I ask some people, which one is good? A lot of people say, okay, left and right, whatever, you know? So, but still cannot give me an answer, you know? But just remember this one, easily, the concept, you know? Easy to understand. RHP 0 is good. So, okay, now you know the concept, right? We go to this high pass filter, right? High pass filter, why high pass filter? I thought do two things on the high pass filter. One is concept. You see a pole is 0. We want to understand what is pole and 0, right? And high pass filter will be a very good example, right? You learn about theory, after that, you do simulation on the high pass filter, right? It's always good to learn theory and simulation. You can visualize whatever thing that you learn, right? So look at high pass filter. Can I erase it? Cannot. Okay, high pass filter, you just swap your location of your components C and R here. So it become a high pass filter, right? So maybe just a very quick way or understanding, you know, by intuition, so why this guy pass high frequency signal. Look at this diagram just by thinking, you know.
From what I understand now, for capacitor, when you have a high frequency signal passing through it will behave like a short circuit.
Yeah, because remember, impedance across the capacitor is 1 over SC, right? So basically, as frequency is higher, the impedance go lower, right? When at high frequency, when the impedance go lower, what happens? It behave like a short circuit. That means everything will pass through there, right? This is the very first intuition you can learn about the high pass filter, right? It's a very quick way, right? Now we do the quick analysis on that. Okay, now whenever you do the AC analysis over the transfer function. Transfer function means that we take your output divided by input. It's over we call TF transfer function, right? Or we can say it is a gain. Okay, your output divided by input is a gain, right? So it can be voltage gain, it can be current gain, but in this case, a voltage gain. Very important, huh? And whenever people ask you, you must try to. You don't just say it's a gain, right? Because this gain is very sensitive. It can be power gain. Power gain is in your S parameter in RF, right? It can be a voltage gain, or it can be a current gain. Current gain means that input is current, output is can be voltage or current. Like example, trans impedance amplifier. Your input is a current, output is a voltage. That one becomes dBO. It's very different. Example for current impedance amplifier means that common gate amplifier. Input is current, so your output becomes voltage. So your unit actually is dB ohm. Become dB ohm. Very different. Okay, but this gain right actually is uniless because voltage unit divided by voltage unit become uniless. So tell you have the dB, right? Let's say V your output is voltage, input current is still ohm. So it's still dB ohm. Ohm is still there. Okay, so now look at this transfer function. Right. So how to derive this equation here? V out over input. First, of course, you have this thing, right? You need add together all impedance at the what we call it, this what we call this one denominator. Okay, is this impedance equal to 1 over SC, right? 1 over SC plus R, right? Correct. So how about here? It's just R, right? So now you just multiply by SC, right? Top and bottom you get SCR, and here become 1 plus SCR, right? So what is this tell us?
Got 1 O and 1 0.
Yes, here is 0. What is this 0?
Origin.
Yes, because this is a special word, because it don't have the 1 plus, it called origin or 0, it called infinite 0 sometimes, infinite 0 or pole 0 at the origin. So we have this we have normally have the origin 0 and origin pole also. So when you as far as term always come together, always remember I told you, always remember this term 1 plus SCR, 1 plus SCR, right? Let's say you have more pole, basically you just add together, time 1 plus SCR, everything just time together, because the gain stage you can time, right? Okay, so now you have the 1 0 at the origin and 1 pole. This is not original pole. So that means that you in the transfer functions you plot like this. That means that what I mean by infinite 0? Infinite 0, that means that you have a 0 with the slope of plus 20 dB per decade. It just go this way. It just simply just go up, and the slope is plus 20 dB per decade. It just go up until it meet the pole frequency you set here. No? When it meet, what happen? Become flat. So this is what we call a cut-off frequency. It means that now it pass all the high frequency and filter out the low frequency. Right? You can see that all is come from the formula. Right? That's why a high pass filter, there's 1 0, there's 1 pole. Actually make this function. Right? So now you want to look into the simulation. A quick way of simulation on this. That's why I said it's good to do a simulation. So all of you can see it directly from the simulations. Okay, where is my LT spice? Here. Right, a very quick one. Okay, for those that are not familiar with the LT spice, you can learn a very quick way. Because I found that LT spice is the most simple software you ever can learn. I forgot. I need to move first, right? Move. Okay, then I can rotate. Okay, so now you have a capacitor here. Okay, sorry, it's a wrong way. Okay, I need to move. Sorry. Move. Now we are doing the high pass filter. So your resistor here to move. After that you rotate for a while. Okay, now we got it right. So okay, and then you need a voltage source. We want to see it. It's not hard, so it's a very quick way to learn this LT spice software. Right, now here I can connect here. Okay, here put one unit because you need AC signal, right? So put AC one here. Maybe I can ask you later why AC one. So I put AC one here, right? So what is our? I think you do put some label there. Let's say we out. Okay, put some this they put what? 1 micro, right? 1 micro. So remember what I cut off frequency?
1K.
How accuracy?
166 kilohertz or 166 hertz?
160.
166, right? Okay, never mind.
No, 159.
Spy analysis is just AC analysis. So type out is decay. So 100 point. So start from 1 hertz to maybe 100 meg, right? Right. So after I do a simulation, right? Okay, come out. So plot the output signal here. Oh, nothing happened. Okay, you know why? Because there's a short circuit here. Okay. Right. So, okay, now come out. So I think you can see very clearly, right? I think at first, what I think we want to find from here. First, we look at. I think a few things we can learn from here. First, you look at the slope, right? First, you look at the slope. You find a slope here for this one.
What is the second curve behind the?
The one is phase shift. The dotted one is phase shift, right? So you find a slope here, but hopefully it's okay. Well, I think it's about that. Okay. Because they already almost already meet the zero there, about 18 dB, 18.5. But if you put here, should be fine. I think if you put it here, put lower a bit, you get a 20 dB per decade, right? This is zero with a 20 dB per decade slope, right? This is the first thing you want to learn here, right? So after that, look at what else you want to learn. The cutoff frequency. Where's the cutoff frequency? Look at minus 3 dB, right? I need to go down a bit. Okay. Okay, what is it? About 160 lah.
160.
What is the phase shift?
45.
Yes, go forward. Right. So look at the phase shift. It starts from 90. You start from 90. After that, when there's further, you go to zero. The phase shift of 90 degree. It starts from 90 first. Okay. After that, the more phase shift. Right. So you understand the concept of the high pass filter. This is called infinity zero. After that, there's a pole there. It becomes a 0 dB. Is it easy to learn? No. So I think that's why I said you learn in this way, you can remember, right? Right? You don't just study high pass filter. You study about definition high pass filter. High pass filter is to pass a high frequency signal. I think the message will forget already. Right? No? But when you learn, you based on understanding. Okay, based on this one, you derive the formula. After that, you know that, okay, high pass filter there's a 1, 0 and 1 pole, and you prove by the curve, you can draw the curve theoretically. After that, you can do a simulation to understand it, you see exactly what happened. I tell you next year you can remember about it. Right? So this is powerful how we can learn things. Human, we learn things by seeing the image. I do a study on that. Image is very powerful. People can remember the image more than the words. Right? The image, whatever image you see here, you can remember it. But talking about number, talking about the theory, people easily forget about it. Right? Human only memorize by image. right? That's why when I do a lecture, right, you know, I will give the image of the learning to the students so they can remember it. Instead of just put a lot of theory, many slides. No, you see a lot. Sometimes lecture a lot of slides, right? More than 100 pages. You know, but no point. You can't remember it. You know. And then I always stress also on any of my company design review. You know, I tell my engineer, don't put too many slides. People can't remember it. Okay, put the important slide on it. Right? You put so much, people you load up with too much information, people can't remember it. Right? You put only important information. Image, interpret the curve. This is another thing. Right? If my requirement for everyone, you know, as an engineer, you know, actually a graph without interpret the information, it is meaningless. You know, I remember I got one engineer, you know, send me a result. I think the PowerPoint more than 200-300 slides. All the graph. So at first it's very proud, come to me. Hey, I done everything, all the summation. When I look at the result, I told him, you give me 300 pages, but I don't know, I have to study one by one to interpret the result. I told him that you have to do again. Because never interpret the result. You can do many estimation, you give you many waveform, but you don't interpret the result, actually meaningless. Right? Sometimes we see the result, actually we want to see what you interpret from that. Is it good or bad? No? You don't only interpret, you interpret the result and analyze, is it a good result or bad result? After that, you put conclusion, you know, a summary, what we get from the design. You know, what is the risk based on the waveform. You know? You just put 300 slide waveform without interpretations, actually it's meaningless. You know, we can ask any engineer to do that, right? Because all us we learn about theory, we need to interpret. You know, that's why I say interpret. You know, you can interpret. Okay, this guy actually there's one pole, there's 1 0. There's a phase shift. Okay, and this is a high frequency filter, right? So all these things you learn what maximum is 90-degree phase shift. All this, you know, will give very important information to them. You get it? No? Understand? Any question to ask about this high pass filter?
Yeah, so in this case, right, the zero here at the origin, is it right hand pole? Because like when you go up the slope, it will be like plus 20 dB, but then your phase shift will decrease over time. So in this case, it will be a right hand pole.
It should be right hand.
Okay, right hand pole.
So look at equation. It can be add on. No? Let's say you have another 0, it become 1 plus SCR, right? So you have another pole equal 1 plus SCR again. So the same term you can use. You just add on, type together how many pole and 0 you have. Like this I call it transfer function, right? You add on, right? And this is what we call 0. You know? Like let's say you have another pole, we call it SCR again. So normally how you find the 0, you just equal to 0 here, equal to 0 here for individual. You find the pole and 0. Then you can find out what's the cutoff frequency. Right? This is for you to find the cutoff frequency equal to 0.
From the equation, can we tell if this one is actually that up pole or the right?
Actually, you see here, actually this one you can tell directly, but this one is plus, right? Definitely is negative, right? But for here, this one is very hard to tell because the equation is show is 0, right? But here you can easily tell as long the answer you get negative, that means it's a good one. Good one we normally call left, right? Right? But back to the answer question just now. I'm not sure is it got left or right for the origin.
Oh.
You mean here sound right?
Yeah, from the origin. Because based on the definition that you said earlier, for right hand pole, you said that it is like plus 20 dB per decade, and then you also you have to minus. I mean, like the phase shift will also decrease over time. I mean, sorry, when you vary the frequency towards the right side.
But this one I need to check. I need to check first. Because this one confirm no. Anything your equation after that you get as a negative is a left. It's stable.
Okay.
I think you get positive is not stable. I think on the right side. But I'm not sure about this one. Do we consider a left or right for this origin pole and zero? For me, maybe not at all. I need to check on that.
Because if there is one, the gain of this one, then contribute to the phase which is 1 decade earlier. But if this is starting from 0, then there is no 1 decade earlier. So you cannot see the effect.
This one. Okay, because this one is always start very early. This is very early. It means that even the second pole, this pole haven't come in already started.
No, I mean without this one, with just this thing, then the phase of this one also should start 1 decade earlier. But this one should be starting at the origin, right?
You start at origin. You start at 90 degree.
No, I mean for the frequency of this one, you start at 0 frequency.
Start at 0 frequency.
So
I mean that
phase of
for origin pole, it start at 90 degree first.
Oh, okay.
Remember the phase short loop? We had an S square, right? Remember the PLL? Okay? You start from, you still remember the curve, right? You start from negative 180. You still remember that, right? You start from negative 180 because of the double pole, double origin pole. You start from minus 80 straight away. If let's say it's a single S only, you start from 90 degree, minus 90. That's why the PL it can be stable because it has minus 80. After that, there's 1 0 coming in. Now, if you look at the curve of the PL phase shift, look at, you still remember, you start from something like this, minus 80, right? After that, there's a pole, there's a 0 there. So it makes the system stable. This let's say this is a UGF. Okay? So it makes the system stable. Okay?
One question. Back then during the low pass filter, right, when we tried to do the simulation, then the phase shift always starts at 90 degrees as well.
90 degree.
90 degrees also.
90 degree.
After that cut off frequency, it will start to decrease.
No, start from 0.
Start from 0.
Start from
For the phase shift.
Yeah, start from 0. So you compare start from 0. Let's say I simulate for you and see. Actually, you see, okay, I simulate for you and see. Let's see. Is that interchange location?
The C1 is still open circuit, I think.
So you look at here, start from 0. Actually, for okay, you see, remember this is start from 0 and coming down, right? Because this is called phase shift, right? For high pass filter, very different. Let's say I come back again. I think I just undo.
F9 multiple times.
F9.
But there's a button there also, like when you move the thing, there's actually an arrow there. Move to your right.
All the way to the
Oh,
right.
I see.
Oh, this one.
Yeah, yeah,
Oh,
yeah.
easy.
Okay.
Same, huh? Okay, now, okay, what the meaning of this? You see, actually, when it close to here, it means no more phase shift.
Okay.
Okay, it is like I mean here it means that actually, although we look at here, actually it means that here actually there's no more phase shift. Okay, here there's a phase shift. It means it start with the phase shift up.
So the fishy
Okay, when the input frequency near to the cutoff frequency, the phase shift becomes lesser and lesser. It's opposite from the low pass filter.
Oh, okay.
You get a point?
That's it.
Because when if the signal is passing through the filter, right, that means the phase, when it can pass, it means the phase shift will be very minimal.
So it means that if your frequency is like moving away from your car frequency, then your phase shift will actually become more and more.
Yes, example in this case, right, let's say you operate at 10 Hz, right, your phase shift will be 36 degrees. So it will increase the input frequency, your phase shift become lesser and lesser. I mean at the end of the day, here, right, it's just overlap. Overlap one another, input and output overlap together.
So in this case, when it approaches the car frequency, then your phase shift will actually get lesser and lesser.
Lesser and lesser.
Okay, understand.
So that means that it depends on your whether it's a low pass, high pass. In high pass, you go in this way. At low pass, I mean that you further away from car frequency, the phase shift will be more and more. Right? Understand that concept? Okay. So now I think, no? We have done. I think our lesson until now. Okay, we'll finish this high pass filter. And I really hope that all of you enjoy the class for just now, learning about the low pass, high pass filter. So I think it's a very interesting lesson. Okay, I think you can get insight of how the phase shift moving, what is zero and what is pole. Practically, not only is in your mind, but you can see from your eye, how the phase shift is going on with the different input frequency, right? So I still have another three more minutes. 3 more minutes. So any question to ask? Q&A question here. Because we go for another break. Okay, we will complete the class by 11:10. 2 more minutes.
This high pass filter, right? In actual world, where we use
Okay, two applications. The first one is really work as a filter. That means that remember the PLL? There's a high pass filter there, right, in the closed loop. Okay, you filter out the what we call it, the noise from VCO. This is the first thing. This one is more to signal processing. The second function is for your negative feedback loop stability, right? And we create this what we call it LHP 0 to neutralize the pole that in the closed loop. So we use that 0 to reduce the phase shift. So there are 2 applications. One is for signal processing, right? Like I mentioned, signal processing means that filter out the low frequency noise, like flicker noise, thermal noise. The second application is more to the negative feedback in the closed loop to introduce 0 to neutralize the pole, or I could say that to reduce the total phase shift by introduce an LHP 0 there. So basically these are 2 main applications of the we call it high pass filter, or in signal processing we call it high pass filter, right? We call it high pass filter, but in the negative feedback we call it 0, the small signal. So it's a different way of definition. Okay, that's good. I think I will learn, and then we come back again after our